We're continuing our lesson on polynomial functions. And so I just want to go over some basic features of the graph. So one of these we've already talked about. But the graph of a polynomial function is going to be continuous. There shouldn't be any breaks or holes in the graph. Let me spell that right, sorry. All right, and a polynomial function graph is going to have smooth, rounded turns. Oops. All right. Now today we're going to talk about end behavior. It's one of the things we're going to talk about. And end behavior depends on the degree and the leading coefficient. So it's important that you know what those are. So the degree is going to be the largest exponent of the polynomial function. And then the leading coefficient is going to be the coefficient of the variable with the largest exponent. Okay. And the leading coefficient is always going to describe the end behavior on the right. So when we're talking about end behavior, we're talking about basically the directions the arrows are pointing. And so leading coefficient will tell you what's happening on the right. So if it's a positive leading coefficient, it's going to be pointing upward on the right. And then if there is a negative leading coefficient, then the arrow on the right is going to be pointing downward. Right? And then to figure out what's going on the left, you have to know if the degree is odd or even. So if the degree is odd, the ends are going to point in opposite directions. And if the degree is even, the ends are going to point in the same direction. Okay? And so try to remember that the leading coefficient tells what happens on the right. So if in this first table, if there's a positive leading coefficient on the right, I know for sure the graph rises to the right. And then if the degree is odd, the left is going to do the opposite thing. So the graph falls to the left. Okay, we're going to move over here. If there is a negative leading coefficient, I know on the right the graph falls. And then for an odd degree, the left is going to do the opposite, so it's going to rise. All right, then even degree, the ends are going to point in the same direction, so it makes that a little easier to do because the right and left are going to do the same thing. So positive, I know on the right, that means it rises. Even degree, the left is the same, so rises left and right. And then even degree and negative, it falls left and right. All right, so on example 1, we're just going to describe the end behavior. So immediately on A, I can see that there is a negative leading coefficient, so I automatically know that this graph falls on the right. And because the degree is even, 8's an even number, it also falls on the left. Okay, and when I go to the next one, I can see that there is a positive leading coefficient, so I know it rises on the right. And then this one has an odd degree, so that means that the left does the opposite, so it falls on the left. All right, and we're just going to go through a bunch of terminology. So a polynomial function with degree n, so just whatever degree you want it to be, the function has at most n real zeros. So the number of real zeros, the most it could have, matches with the degree. And then the graph has at most n minus 1 turning points. And so there's one less turning point at most, possible turning point than the degree. Okay, and so on the graph, the zeros are going to be the x-intercepts. And the relative max and the relative minima are going to be the turning points. I'm having a serious spelling problem. Okay. All right. And then all of these following statements are true. So if we know x equals a is a zero of the function, that means that that's a value for x that we can plug in, makes the function equal to zero. Then we can also say that x equals a is a solution to the polynomial equation where that function would equal zero. We would also say that x minus a is a factor of the polynomial f of x, and that a 0 is an x-intercept of the graph. All right, so zero, solutions, intercepts are pretty much, and roots. We could also say roots for those. All mean the same thing, and then we can also take that and talk about how it's a factor. Right. So on example 2, we're going to use that idea about a factor. We know the zeros of a polynomial function, and on the second part, we also know the multiplicity of those zeros, and we're going to find a polynomial function that has the zeros. It's not going to be the only polynomial function that has those zeros, but it will be one that does. So if 0 is a 0, then x minus 0, or just x, is a factor. If negative 3 is a 0, x plus 3 is a factor. And then for negative 7, x plus 7 would be a factor. All right. So that's the beginning. Now I do want you guys to multiply these out. That is a polynomial function that has those zeros. Okay. The next one is slightly different. We still know the zeros, but we're also given the multiplicity of them. So even though it's in a different order, I am going to start with the 0 that is 0. So I know that's going to be x. But if it has a multiplicity of 3, it's actually going to be x cubed. All right, and then for negative 2, it's going to be x plus 2. And then for 3, it's going to be x minus 3. All right, and then I'm going to multiply those together. And that's it. There's one of them. It's not the only one, but it is one of them. Okay, and then this last one, we're going to bring everything together. We're going to bring together multiplicity. We're going to bring together zeros, turning points, graphs, end behavior, everything. Okay, so we are just given the function, and we're asked to find the real zeros. So to find the real zeros, we're going to need a factor. So we would start by factoring out a common factor. which is just going to be x squared. But since that leading coefficient is negative, I'm going to factor out a negative because it will just make it easier for us to solve from there. I don't know if I talked to you guys about the Prizer rule of 4 before, um, but it's a kind of something that I remember. There was a teacher here named Miss Prizer that told me it, and so that's what I call it for her. But if this leading coefficient is 4 and this middle term is odd, then it's definitely going to be 4x and x to get the 4x squared. If this is 4x squared and this one was even, then we would do 2x and 2x there. So it's just a little bit of a shortcut to help you factor. Now I know my sons are different, and there's not too many ways to get 21. Most likely it's going to be 3 and 7. We just have to figure out where to put the 3 and where to put the 7. But this looks like it should work because that's going to give us negative 12 plus 7 is going to give us the negative 5. All right, so that makes our zeros. Once we get it in factored form, we should be able to just look at the factors and tell the zeros. So our zeros are 0, negative 7/4, and 3. Right. The next thing it asks us to find are the multiplicity of each of those zeros. So I gave you more room than you needed, but I'm just going to draw an arrow. All right, so the 0 came from this factor, which was being squared. So it's going to have a multiplicity of 2. Right. The other two zeros were not repeated factors, so they're going to have a multiplicity of 1. Okay. And then determine the maximum possible number of turning points. So that's what we talked about on the front, where the number of possible turning points is 1 less than the degree. This one has a degree of 4, so the maximum turning point should be 3. Okay, so let's look at this graph. Now, our graphs are going to be fairly accurate, but mainly the zeros, the end behavior is going to be right, the turning point should be right, but not at the right place. So anyway, I know I have a 0 at 0. I know I have one at 3. And then negative 7/4 is slightly less than negative 2. Okay. Then let's talk about this end behavior. So our leading coefficient is negative. So I know on the right we're going to be falling. But because the degree is even, then this one is going to fall left and right. And I'm going to go back to the multiplicity because the 0 at 0 has a multiplicity of 2. I know my graph is going to bounce there on the x-axis. It's going to touch, and then it's going to go back the other way. Okay, so falling on left and right, I know I'm going to have arrows pointing down, so let's go ahead and do that. Okay, then a multiplicity of 1, I'm just going to go straight through like a line. All right, I'm going to go up. I don't really know how high, but that's okay. And then I'm going to bounce at this one. I'm going to go back up and then go through that one. It's a little wobbly, but it's pretty good. Okay, so now your assignment is just going to be the worksheet.